Okay. So hi everyone, I'm Constance from the International Research Institute of Disaster Science of Tohoku University. So as you can see here, our guest speaker for today, Anawat Suppasri, is the same. We are from the same lab, and technically he is my boss. So I'm here to introduce him. So I just want to briefly mention the history of the International Research Institute of Disaster Science. It was established exactly 10 years ago in light of the 2011 Tohoku tsunami. And what I think is that the mission was to improve disaster risk within the country and also our understanding of the disaster risk globally. And with regards to our lab, we also try to improve our understanding of tsunamis, not only from the engineering perspective, but also from the social perspective. So I'm not sure if you guys already know Anawat, but Anawat was his more popular works were on the building fragility from the 2011 Tohoku tsunami, and since then we've been developing more databases and case studies of vulnerability from tsunami. So I will not talk even more. I'll let Anawat introduce what have been our progress since the start of the tsunami engineering lab in Irides. Anawat, the floor is yours. Thank you.
Okay, thank you. Thank you so much. Yeah, you speak. I think I don't have to introduce myself anymore. But I mean, yeah. So, but today I think I would like to make the talk more broad. So, as I put in my title, I would like to introduce you broad area of hazard and risk assessment, targeting tsunami in particular hazard. So I'm sure that in this series of seminar, other has been already covered different topics. So today I would like to focus on my background, which is tsunami. And yeah, so currently I'm visiting in UK in University College London. We are working with that institute who are working. There are many researchers on also social science, which we are still would like to learn more about that. So this is why I'm here. So I'm trying to bridge engineering and science perspective for disaster research. So again, I'm sure everyone knows about the component of the risk, and so my talk today will be shortly stress on each component of the risk. So at the beginning will be about the hazard. So I put some slides about the current research on sea level rise impact on tsunami and how we are facing non-typical types of tsunami, which is non-seismic source. Well, this is recorded, but I would say a few days ago in Japan we have another small tsunami with still still questioning about the source. So yeah, this is kind of our challenge for the hazard perspective. And again, for the vulnerability as well, as Constant has already mentioned, so I have been working on this kind of topics more than 10 years. So I would like to share what has been progressed, not only for building, but other facilities in the sea, marine facilities. And last but not least, this kind of information for the policymaker, they would need to make decision for the evacuation warning, or like an insurance company when they calculate the premium of the loss. So this kind of thing will be integrated, and I would like to share the current situation, what is going on in our area in Sendai or in area nearby. First, about the sea level rise. So as you can see that here, for example, this is already broadcast in NHK TV program. For example, we have 71 centimeters expected rising sea level in this area, but it's not cannot be just linearity. Compared to other hazard, it's more known that okay, global warming or some other impact will be has an influence to other type of hazard. But for tsunami, it will simply more or less on the sea level rise. But from our simulation, for example, in what you can see in the right figure, the blue area shows where we have the situation where we have no sea level rise, but then 39 centimeters and 71 centimeters, how far the water or the inundation can go further. This is show how that the in terms of the area, but in terms of the height as well, it depends on the location, slope, etc. But we can see that in some area the final run up can be double or would say higher than the height of the increase of the sea level as well. So this kind of thing that we have recently start study about the physical mechanism of the sea rise impact on tsunami. This is just one. This is just one location. I show the cross section that okay, for example, when we have tsunami coming, and then yeah, the flow is getting the flow depth getting decreased as the distance and the roughness, but still you can see how far the tsunami can go, or the detail topography is influenced. Well, this is not in scale, but just in case, just to have some ideas about the inundation area, how it can go through the distance. So recently, even in Japan, although we have just start this kind of study, is attract some consideration to local people, including the media. For example, this is a school very close to the sea, where the tsunami 2011 reached this level, where most of the school and teacher they survive within this space under the roof. But yeah, I mean the news reporter, and yeah, we wonder, for example, if in the future, let's say 50 or 100 years ago, if similar situation happens, this kind of situation might be difficult. They might not be survive if we consider the rising of sea level, for example. Also, at the same time, for the flood depths as well, for example, this person he survived in the second floor. His house, his shop is actually like 2 or 3 kilometers quite away from the sea, but so somehow he could survive the second floor. But if we consider the sea level rise, the force of tsunami might be bigger and he might not be survived. So I mean, it's still far future, but this kind of consideration can be start to think about disaster prevention in this perspective. There is also similar study has been done in the past few years. This is one example from Indonesia, where they consider sea level rise in the over top of 2004 Indian Ocean tsunami. You can see simply longer latent period, more far future. We expect higher sea level, and then bigger inundation, which is this is like common sense, just but they represent in more quantitative way. This is another paper from our colleague as well. She also show in another way of representing the information if we think about the probability of occurrence. So for example, the blue line, sorry, the black line shows the case where there is no sea level rise. So we would expect, for example, in one point in this study area in Macau, if the flow depth if we think about flow depth of 1 meter, and in this area we would expect 900 years. But if we have the sea level rise of 550 centimeters, the return period might be decreased to 800 years, or if you think about 1 meter sea level rise, it will be decreased to 450 years, etc. This is just a sample how we convey our scientific data to non-expert, non-scientific people to be more, let's say, easier, to be more understandable way to represent our result. Recently in Japan, I have also have in our team, we have also started this kind of idea. We have tried with the future worst case scenarios in Japan. 2011 was around this area, but in the future also we expect two more cases in the north and in the outside area we call authorized. There are two locations, and this just to show you like, okay, how if we increase the sea level rise for 50 centimeters or 100 centimeter, 1 meter, how far the impact area will be changed. And we also trying to incorporate the economic model so that we can calculate the loss and indirect loss from each type of the different source. Then so by doing this we can know that, okay, with what kind of area, what kind of also from the types of industry, we have a data of industry like agriculture types or service or manufacturing. So by applying this kind of economic loss model, we can also know, okay, which source of the earthquake will impact to what kind of industry more than others in quantitative way. And also this is similar. We just expand our study into the whole Japan. So we have the data for different regions. So we can see, okay, from which, for example, if we consider one source, what region in Japan will be impact the most, for example. By having this kind of data or information, yeah, I'm sure that policymaker or other kind of stakeholders can use to for example, government can allocate the central core budget to each which prefecture should be prioritized, or which industrial or which sector should be prioritized. This is just one some example, some ideas. Second topic on the hazard will be non-seismic tsunami. So in general, for earthquake tsunami, I'm sure you can have more information about that. So we assume the fault parameters from the estimate earthquake magnitude and related fault parameters. But today I would like to introduce you more more unusual type of tsunami, which we recently have been studying. So for example, for landslide, until now in tsunami community we have been doing research on landslide tsunami as well, but more or less it will be limited. It was limited on the like, okay, let's assume that, okay, or randomly for the case of past tsunami, we randomly test the location or the volume of the landslide. Let's say how many cubic kilometers, example, and the area, the size of the source, and then we simulate the tsunami, and then we try to fit with the observational data like the waveform or tsunami height. But recently we are working with geotechnical engineering field researcher, and we are trying to incorporate the topography data, the soil data like friction angle or the slope, and yeah, some saturations situation, groundwater level, and also the earthquake intensity as input parameter to calculate the sliding force against the friction force of the soil. so that we can calculate the possible location of landslide and the depths. So for example, well, in detail, you can I think I have put the list of paper at the end of my PowerPoint, so you can have a look later. So for more detail, again, you can see in this paper. So for example, from this kind of consideration of soil parameters, we can see that, for example, in the case of 2018 Palu tsunami, we could estimate the possible landslide location and the depths as well. In that case, for this case, sorry, we still have no no proof of this, but previous study also suggests that we need another additional source of landslide so that they can reproduce the tsunami in the east of the bay. So in our simulation, we also proved that there should be the landslide in this part of the bay as well. So this kind of agreement between what has been pointed out by the previous study and our landslide simulation result. So it's just to show that we also have checked our simulation with the real survey height. Like you can see our simulation in the red lines, and the point is are the observational data, and also the waveform calculate from the video, also kind of reliable reproduction of our tsunami simulation using our landslide simulation as well. Another example is this what happened last year in 2022. You might recall your memory in January. There was a big eruption in Tonga, and we also, because of the air wave pressure, it generates tsunami to many places over the world, even in the Mediterranean, where there's no water connection to the Pacific, but the air pressure trouble could also generate the wave, and it was observed in many water body in the world. So in order to understand this phenomena in our team also has study about this. For example, but for our case, we split this phenomena into two types. We call local tsunami and distant tsunami. So the first one, we consider the local tsunami around Tonga. So my colleague, he applied his previous study by using empirical way to estimate the initial water level after the eruption based on the assumed energy of the eruption to generate the initial water level, and then we simulate the tsunami. As I mentioned, in detail you can check in his paper. And then yes, so we use the local tidal record near Tonga, and we validate our results. So we could also say that, okay, this kind of thing that we could help to understand the mechanism of the tsunami. However, this kind of tsunami cannot go very far. I mean, in Japan, we also observe this kind of damage. Japan is very far from Tonga, but still, as you can see from these photos, there were like the fishing vessels got damaged like this, or the fishing nets or raft, they were also destroyed by this tsunami. And again, you can see detail in this paper. We also have developed the air and water coupling model to it's like meteor. The idea is more or less similar to the meteor tsunami. We are trying to reproduce the tsunami to Japan, and we're trying to correlate the tsunami and the damage, and try to understand the damage mechanism to these kind of structures. So This is my second topic, which is about the vulnerability part of the research. So as Constant has mentioned, so I this is one of my paper that has been well, we received many citation from the researcher around the world about the building damage characteristics. Luckily in Japan, well, thanks to researcher and the government, that we are good in data collection or this kind of databasing things. So we have large number of building data, and also the dense survey data as well. So we could develop some relationship between the x-axis is the maximum flow depth, and the damage probability in the vertical axis. For on the left is the building damage, different types of building like reinforced concrete, steel, wood, or masonry. Please just forget about the many colors of the curves, but just think about, for example, the red curve. This is the curve for the building to be washed away by the tsunami. So, for example, of course, we know common sense that the reinforced concrete building and steel building should be stronger than wood or masonry buildings, but how or in what way, in more quantitative way. So we use this kind of damage data collected by the case of 2011 to represent this kind of in quantitative way. For example, if 4 meters attack coming to this kind of building, so for masonry they will receive like how many percent, but then you can see much lesser, smaller damage probability for other types of building, for example. Also on the right panel, I show two types of construction materials, and also different types of floor. One floor, two. Oh, sorry, I forgot to write put in a note. So like 1 story, 2 story, or 3 stories or more. So you can see if we have 3 story or more, your curve is getting shift to the right. That means at the same flow depth, you will have less damage. So this also show that how stronger if you have bigger or heavier structures compared in quantitative way. We also have similar things when we consider the types of the the function of the building or the types of the course. So in EOS we also have some difference between the plane course, where we have less flow velocity, where the rear chord is like a V shape of the bay, so it can the flow can be concentrated and the velocity will be getting higher. So at the same flow depth, we expect higher velocity. So that's why at the same flow depth, the building has different types of, well, has higher damage probability in the rear course. Yeah, also the construction year as well. At that time, we have no big difference, because the building cost in Japan is mainly designed for seismic or for earthquake and for tsunami. So this also reflect what has been designed for. And recently, as I mentioned, in 2018, we have the non-seismic tsunami in Palu, which is the earthquake, but then landslide, and then, well, liquefaction, and then tsunami. And then same in 2018, we had another tsunami, which is the eruption from the Krakatau. And for that one, no earthquake, no ground shaking, no liquefaction, but only the short period tsunamis. And we also have the building damage data. So we are trying to compare these two non-seismic tsunami with the data of 2004 Indian Ocean tsunami in Banda Aceh. So we want to see how the ground shaking or the liquefaction or the wave period, how it could impact on the building damage. So in detail, please have a look at this paper. But in general, so what I could say from the main highlight of this paper is that, for example, in as you can see the blue line, this is the one from 2018, the Palu tsunami, which the buildings sustain the very strong ground shaking and also liquefaction. So you can see that even near zero floor depth, we already observed the building damage already. So which is higher than other tsunami events from the same country, Indonesia. But then if you look at the green curve, which is the 2004 Indian Ocean tsunami in Banda Aceh, it has no big liquefaction reported, but it sustained the ground shaking plus tsunami. So that's why it's not as high as Palu with the liquefaction, but still it has higher damage. And then you compare with the Sunda Strait 2018. This one only purely tsunami without ground shaking. That's why the curve compared to Palu or compared to Mandaje, the curve is shifting on the right when we have less initial impact in addition to the tsunami as well. So this kind of thing, of course, we have still have some limited number of data, so you can see the error bar. The error bar is still very big, but at least we can somehow explain the mechanism or the reason of this kind of damage data in more quantitative way. And recently, also related to the work that has been done by Constance as well. Maybe she might want to add at the end of my presentation if she wants. We also trying to focus on the industry where these kind of data, of course, we have tried to split into different types of industry as well, but still it's not has been fully incorporated. So again, industry is more or less different because of the structure itself are totally different that compared to the house or apartment or condominium. So the structure are more or less very specific for each type of the industry, and also the mechanical or facility damage inside the inside the building as well, and as well as the production capacity, the time that they cannot produce their products. So this kind of thing, first we consider about the structural damage of the industry. So again, so please check Constance paper for more detail you'd like to read more. So we also propose different relationship for different types of industry. And also with my student, again, in this paper, we also develop another vulnerability curve based on our interview and some data documented in Japan for the damage to the equipment inside the buildings for different types of the industry, as well as the recovery potential. So we are asking them like, okay, after 2011, how long it takes for them to fully recover. So some might say 1 year, or some might say after 6 months, 7 months, or we ask them when they restart their production, something like that. So this kind of interview or the document we collect in Japanese, so we could develop this kind of data as well, so we can have a look in detail. And again, so I think this is also in my I use this one in my introductory the poster for my talk today. So you can see that we compile this kind of vulnerability curve with the simulate maximum tsunami flow depth from the estimate worst case scenario. So we can see that if we only consider the structural damage of the building, we will get, for example, the damage from let's say 10% to 50, 60%. But if we consider the function, the loss of the equipment. So for example, you can just imagine that if we have the machine or some equipment that in the ground floor, so even 1 meter of tsunami can be already make it well, the electricity or the equipment itself it might be already non-functionable. So if we consider this kind of situation, so even small tsunami can already cause very high damage to the industry as well. So this kind of thing that we still have to, we need more data or need more consideration. And also for this, until now, I just talked about things in land, but if we talk about things on the sea, we also in the past, I also have the data on the fishing boat or marine vessels like this. So we have this kind of data, and we also combine with our simulated tsunami result like this. So I would think I would just yeah. So, but again, the difficult thing for both is that we have no idea what is the exactly position of the boat compared to for building. We know the exact building polygons, but for boat we have no idea where they were exactly positioned at the time tsunami. In from the data, we only know that we only took the data of that they said that the boat was more inside the port. So we just took the data. So we assume that, but still we have no idea which, for example, in this figure, we have no idea which part of the port that the boat was there, each boat was there. So we just we only have to use the average simulated data, for example. But anyway, at least better than nothing. So we try to correlate the hazard and the vulnerability, the damage data to make this kind of fragility or vulnerability of the boat as well. So you can see I also split by the weight of the boat, whether it is 5 ton or larger than 5 ton, or the if the motor or the engine is inside or outside. So we can also see how of course, again, bigger or heavier boat has a trend to have less damage compared to lighter boat at the same height of tsunami or for velocity. Again, for 2011 tsunami, we also have a data. I think I would like to explain from this slide first, and I will go back later. Yes, so from the satellite image, again, you can have a look in my paper. From satellite image, from previous study, we can see the situation before and after tsunami. For example, if we focus on in this area, you can see that this kind of aquaculture raft. This is actually the tsunami entering this bay in the lower left, and of course higher flow velocities is expected in the lower left, and then getting smaller to the end of the bay into the lagoon. So you can see the comparison between the left and right before and after. You can see that some of the raft has been destroyed or washed away. So we use this way to count or interpret the damage situation. And also from the satellite image, we can also detect the area, the green is the eel glass before and after. So we can see also this one. So you can see more eel glass has been destroyed near the entrance of the bay. So you also use this way to interpret the damage data of the eel glass. In this paper, we only consider the simulation of water. So it can be like in this damage pattern. But recently, we also considered the sediment transport simulation, so that some eucalypts might be uproot like this from the scaling, or might be deposit like this. So this kind of two phenomena can be has been already reproduced now. But at the time of this paper, we only consider the flow. So and then yes, so we do simulation here. So we can we can simulate water level and flow velocity. Also, as you can see that we expect higher flow velocity near the bay entrance. This is on the right panel. This is another study area. But anyway, so again, so by doing similar things, we can also have some quantitative way to explain the damage to this kind of thing to the U class, and also for the rough aquaculture rough as well. So then this kind can support the risk assessment. But as I mentioned, in 2022, last year, the damage to Japan based on the Tongan tsunami. So we also have collected the damage data to the oyster or seaweed draft. So we are trying to also understand what is happening. So until now, we know that for this kind of the aquaculture raft, if the flow velocity is higher than 1 meter, no matter what how high the water level is, if we have faster velocity than 1 meter per second, we will have definitely damage to these kind of structures. So from the last year tsunami, we also have the data. This is one bay we call in Yamada Bay. So we also have the data that okay, this is the bay entrance, and the polygons name in Japanese show the name of, how to say this, it's like the way of aquacultural area. So this one show that in this area, this is the most area. These are two areas that there were some damage report by like 10 to 12% of the damage to the raft. So again, so we from the simulation, we simulate the flow velocity and water level inside the bay, and we plot similar thing. Well, we have two types of the raft. Well, is like the raft type or the long rope type. But anyway, so we have similar result that, well, it's like if we have 1.4 meter per second, that the damage will happen. But still, we have to revise or improve accuracy of our tsunami. But somehow the damage and non-damage data show more or less similar trend of what we have known so far. We have also applied the debris simulation, the floating simulation. Although at the moment we haven't consider the anchor of the raft yet, so we just simply model as a floating things on the sea surface. So, but from the simulation as well, we can see that for the area where they have no damage report, the raft only move, for example, in this place, move only 55 meters, but for the place where we got damage, the raft moved like 3 times longer. So that means if it moves longer, it has more drag force to drag the anchor, so that the raft itself has been shifted, or the rope might be torn, might be cut by the tsunami power. So this kind of thing is still undergoing. We are now trying to consider the weight of the anchor to this model as well. Last but not least, I think I will spend my last 5 minutes to explain about, okay, in summary, we have until now we have been studying about the hazard and also the vulnerability. But then when we think about the policymaker or the end user, like for example, the industry owners, so what is going on, what is actually their needs. So as a researcher or as a scientific expert, um I think it's not only applied for tsunami but for other types of hazard as well, how we could manage or reuse our scientific data. So for example, well, in tsunami community, we have been study a lot on we call PTHA, probabilistic tsunami hazard assessment. So for this kind of study, we will give them, or in the paper, we will say something like this graph. Let's say, for example, how high of tsunami height, and well, like annual accident probability, or how likely 5 meter of tsunami, how likely is 10 meter of tsunami will happen in a year or in a near future, whatever, based on different types of uncertainty. Or we show them like the hazard map of tsunami from different periods. But when we talk about the policymaker or stakeholders, industry owners like that, they have different perspective. For example, when they saw this graph, they have no idea. So what they should do? If the earthquake happened in this area, do they have to evacuate? Do they have to stop in their production, for example? So this is another dimension that actually the stakeholders really need to see or to understand or to have for their so that they can make decision. So for example, recently with our student, we also have tried something a little bit different. For example, we model tsunami from assume earthquake source around Sendai port like this, and we would like to know, okay, so in Japan, if we expect tsunami more than 1 meter, the government will have to release the tsunami warning issue. So we would like to see which location of the earthquake will definitely generate tsunami to reach that warning level or something like that. So for example, from this figure, we can see that if, well, depending on the types of earthquake that we parameter that we assume in our simulation and the shape of the Sendai Bay or some etc. But at least for this case study, we know that okay, if the earthquake of magnitude 7, if it is if they occur in this red area, it will definitely generate tsunami that reach the tsunami warning to Sendai port, to Sendai city, because Sendai port is the way that we consider for the warning. Or if it occur in the blue area, we can be safe that okay, the tsunami will be less than 1 meter or something like that. Or in the yellow area means it depends on the angle of the earthquake. So this kind of information, we believe that this, of course, we do similar thing for this for PTSA for the way we produce this kind of simulation, but I think it just depends on how we represent our result, so that in this dimension we can also help the local stakeholder, policymaker, so that they can have better decision making in the future as well. Recently, this is one of two, almost my few last slides. We are we have we are tackling some problems with the kind of how to respond in case of tsunami warning with these stakeholders. So yeah, we have universities, Tohoku University Rolling Club, which they are using one artificial canal all around this area, The blue area show the inundation area, and the colors show the tsunami height of 2011. So they're actually doing the training around here inside the tsunami zone. And also we have Sendai Airport, which is around here, which also in inundation zone. And also we have the Air Self-Defense Force in the inundation zone as well. So they are now, like after 10 years already, so we are already back to normal lives, but still we have to be aware of the tsunami warning. But yeah, but the thing is, this is that is happening right now is that in Sendai actually we have the seawall. Before 2011 it was 6.2, and then after that we increased to 7.2. But in Japan, the criteria for tsunami warning is that if less than 1 meter will be tsunami advisory, if 1 to 3 meters will be tsunami warning. But still, you can see from this diagram that even they issue tsunami warning. I mean, when they expect 1 to 3 meters, still actually the expect tsunami height still like double smaller than the height of the seawall. But I mean, in terms of the word, tsunami warning has been issued. So local people or other stakeholders, they feel like more unsafe, right? So again, still is questioning. Still, we were discussing with these, for example, these stakeholders. So we know that the fact that we have physical protection, like 7.2 meter in front of them, but then in terms of the way the government have to issue, the criteria is more or less different. So I mean, now we have no correct answer. Okay. If we talk about, okay, we know that, okay, if we say warning, so it will not be over top the seawall. Actually, you don't have to do anything. You will be protected, but in the reality, people would, when they hear the warning, they would like to evacuate. So this kind of thing, I think, there's no correct or wrong answer, but it should be discussed for each stakeholder, how far they understand the situation, or how much they would like to play safe to make more like conservative conservation countermeasure. So again, I would like to end my talk with this kind of questions. So maybe if you would like to consider this, we would like to discuss during the discussion time, or again for other types of hazard. Maybe this is only exceptional case for Japan where we have many structures, but maybe in the future or in other types of hazard we might have some small conflicts between the coastal defense, not coastal, I mean the protection, and also the warning criteria. So I think this can be should be this study or discussed more in the future. So I would like to end up my talk with showing these publications. You can also check my website. I have the full list of publications, so you can read more detail and about what my talk for each topic later on. Thank you for your kind attention.
Thank you, Dr. Suppasri, Anawat. So, are there any questions from the floor? I know it's a very long presentation. Thank you for covering all the works of our lab from the last 10 years. So I know there's a lot of contents, and probably some of you might have questions from individual projects that he
Yeah.
has mentioned.
Yeah.
So
Right.
if you want to, can you just either on your video or raise your hand? Are there any questions from the floor? Because I think it's a wide range of issues. It might be something that are applicable to each of your own research field.
Yeah, I think even I use the tsunami as an example, but I'm sure that it can be applicable for other types of hazard as well.
Mm.
And
Are
I
there
intend to
any?
be very general so that I can cover many topics and you can read more detail from each paper.
Yeah. So you can also write down your questions in the chat. If not, you can turn on your mic or turn on your video to ask the question.
can put, let me search my website and I can put my the link to
Mm.
my my homepage so that the audience can go to read the paper later in detail. Just while we are waiting. Or Constant, you have any question to me? Of course, we can discuss later, but or
Of
yeah,
course, we can, of course,
whatever.
discuss in the lab. But yeah, actually, I wanted to ask for the first few slides, the one on the sea level rise. I have no idea if you have mentioned before what the area, yeah, of inundation is, the case study.
Oh, that is in the west of Japan, in Fukushima and also in Kochi Prefecture. In the where we expect the Nankai tsunami.
Mm.
Yes. Oh,
So
the
we have a question from Jose.
well, for it's yeah, it's owned by also our professor. So we normally we share by upon request. So yes, for the tsunami simulation, the typical earthquake tsunami simulation. So we yeah, upon your request, we share. Actually, the code has been shared or has been used for since I think 20-30 years ago in many
Mm.
countries. Mm.
So if you want the code, you can just reach out to anyone in our lab and then see if we can help you with it.
Yeah.
Mm. Okay. Are there anybody else who have? Okay. How long in advance of a forecasted level are the warning issued? This is from Isabella.
Okay. Thank you. So yeah. So okay, let me read. Okay. So in Japan, sorry, I don't have in my slide, but I can explain that. So they could observe the earthquake data within 2 minutes, and is the JMA, Japan Meteorological Agency, responsibility that they have to issue tsunami within 3 minutes. The first warning message should be issued within 3 minutes. So after the earthquake. So the problem is that, for example, in 2011, the earthquake was magnitude 9. So I was there and I experienced the shake. So even I feel the shake like 4 or 5 minutes. So that means JMA has only 2 minutes to observe the earthquake data, which is like, I would say, just 30-40% of the earthquake. So they couldn't catch the whole um, data, but then they have to release the warning within 3 minutes. So that means for scientific perspective, it is straightforward that we have less record observation. That's why we underestimate the tsunami warning at the beginning. So, but then after that, we have some buoy or GPS observation in the deep sea. So we know that okay, that earthquake was the tsunami was so big, so we increase we upgrade the warning. So to help to improve or to solve this problem in the future, right now we have already deployed 150 more sensors that cover the area until the east side of the Japan Trench. So it's very dense sensor network. So again, we still have to rely on the pre-simulate database. So many million case pre-simulate in a database. So after earthquake happened, within few minutes, we have to issue the first warning. But then after that, we can use very dense observational network sensors to check what is the really height of the tsunami, and then we can support or improve the warning.
Hmm. I also like to add, like what we observed in the 2016 Fukushima tsunami is that the warning was higher in the first. I mean, yeah. So the first warning might differ from the second warning just because in our database it's what we pre-assume to be the earthquake scenarios, but there are other more local factors such as the amplification of bass or resonance that might affect the tsunami wave heights that eventually comes onto the shore. So this also affects the warning that was being issued and subsequently being issued. Yeah. Are there anything else that anyone would like to ask?
I also would like to add a little bit, as I mentioned about the newly deployed sensors. So having that things, so it's of course it helped to improve the accuracy of earthquake, tsunami, of course, but also we sometimes we also use that information for the real-time simulation. But it also help, for example, in case of Tonga tsunami, because this is non-earthquake source and come from far away from distant source. So even no tsunami happen, no earthquake occur, but then we observe the sudden change or abrupt change of the sea surface. So we can also apply this kind of network, observational network for non-seismic tsunami case as well.
So, are there any more questions? If there are not, I'd just like to make a few announcements. So, for our AOGS Coastal Zone Working Group, we have just been recently established, like in the past year. So we also like to gather more members to join our working group. This is just to also improve our understanding of coastal hazards within Southeast Asia. So this is also part of AOGS. And another thing is next year there is a AOGS conference in South Korea, and it's around I think June. So if you can, please submit your abstracts there. And there are also ocean sciences as well as IG session where you can submit coastal related presentations. So I would strongly encourage you guys to join those. And also the coastal working group is also thinking about setting up a session for panel discussion. So if you're interested in suggesting some topics, please reach out to any of us from the AOGS Coastal Working Group. So the link that was sent to you guys, you can email them if you have any suggestions for the next year AOGS panel discussion. If there are no other questions, I would like to end today's presentation. Yeah. Thank you so much, Anawat, for today's presentation.
Thank you for giving me a chance for this. Thank you.
Thank you.
Thank you. Bye bye.
Okay, bye-bye.
You. Thank
Bye,
you.
everyone. Thank
Bye
you.
bye. Thank you.